Good day. So we on to design exercise 2, where we are required to do some calculations. Right, so the two calculations we're going to look at and which will be applicable for your first project is stability calculations. Right, so stability calculations and strength calculations. Right, stability has to do with the entire thing toppling over. So for example, if we push in this cart, then will it, when loaded, will it tip over? Right? Will it tip over above these wheels here if we push in this direction? Right? So that's what stability checks is about. And the other one is the strength calculation. So this is to ensure that the members themselves, in this case, we say that we're using a pipe section or pipe to as the member. So we want to ensure that the stress is not too large, not large enough to cause failure. Right? As we go forward in the course, we could see that stress is not the only measuring of if it will be fail, if it will fail or not. Another thing to look at is how much it deflects. So if it is we load it up, the stress, it will be safe stress wise, but it could be that it might sag too much and be an issue. Right? But we will come to that later on in the course. Right now we're looking at stability toppling over and getting a handle on the stress distribution or the stress in each member. So the first thing we're going to look at is stability. Right? So we said that we pushing this thing, we applying a force, let's say over here, and we're moving the entire thing forward. So what I'll do, I'll draw this on the side view. Right, so feel free to fast forward at certain points when I'm drawing and stuff. Right, so we're applying a force, FP is the pushing force. And we're saying that this force acts as a distance h from the ground. Right, so in the extreme case, we are saying that we have a load over here. We call that FL for load, and it's being at the most extreme, which is the outermost. Right, so let's imagine we have this basket here being loaded the most. Right, and that distance, well, we saw from the diagram that we indicated some dimensions, 0.5 meters. So this distance is 0.5 meters. So the base, we have it here as L because we don't know what the lengths are as it. So this is the base here, L. Now if we pushing this forward, if this has a tip over, more than likely it will tip over about this point here. So this will be a tipping point. Right, so if it is the friction is too high or something, and you're pushing FP, the entire thing might just spill over like that. Right? So we need to determine now what is an appropriate distance L such that when we apply a tipping force, or when we apply the pushing force FP, that it will not spill over or turn over, as the case may be. So we need to determine FP then. Now everything will be done parametrically, meaning that we are not using numbers at this point. And the reason being is that as we move on, we would see that certain things might cancel off. So for example, FL, we will keep FL as FL. We will not put 45 kilograms as in description said that that is a load it must be able to carry. We will keep it as FL. We will keep the height as H. We will keep the distance here as L. But we know for a fact that this is 0.5, so we keep it at 0.5. Right? We are saying that the rear wheels are up, so it's about to tip over. So the rear wheels, these two wheels, they are off the ground. So that means now that we have the friction force that is opposing is applying in this direction. So that's F. And then we have the reaction force. Right, so the reaction force therefore would be, remember we have FL acting down. And we have this was FP being applied here. So the reaction force therefore would be FL on 2. There's just two wheels. So we could say here that the friction or the frictional force is mu by R, which is mu by FL on 2. Right, so we will come back to that over here. So we could update the diagram here and said, okay, we have frictional force R is equal to FL on 2, and then we have that as reaction force, the friction be in this direction here. Because we have to mu R. Right, so mu is the coefficient of rolling friction. Right, notice it says rolling friction. So if we look at the diagram and we take resolve forces in the x direction, we say Fp minus, now remember it's F and F, there's two front wheels, so 2F is equal to 0. So that means the Fp is really 2F, which is 2 mu R, just 2 mu FL on 2, which works back down to be Fp is mu FL, which is what we expected. Right, so this is the pushing force required. So the next thing we're going to look at now is taking moments. So we're going to take moments about the tipping point. So we had said that this was here was the tipping point, and it's where we're taking moments about. So our distances for taking moments, we say that this distance from here to where we want to take the moment about is L minus 0.5, and then the distance from Fp to the tipping point here, well, we said that distance is h. Alright, so let's bring this across here. So we can have a look at it when we're taking moments. So we're taking moments about the tipping point. Right, so we call this tipping point, we call this point A. So we say moments about A is equal to 0. So we start off with the anticlockwise moments, which is FL times the distance, which was L minus 0.5, minus the clockwise moment Fp times h is equal to 0. So we end up with FL remember Fp was mu FL. So we could substitute that and say that FL, FLH. So that's what I was talking about by keep doing everything parametrically. You notice the FLs could cancel. So we do not even need to load to know if this thing will tuple or not. So L minus 0.5 is really mu by H. Right, so this is our fundamental expression in terms of expressing the tipping point or the tipping characteristics. Right, so take us go back here now and look at something. I had said equal to 0, right? But if we were to rewrite this now, and we said that in order for this to remain stable, the moment that caused by the FP, right? FP is the hand force that will cause it to rotate this direction as a tipping. And the stabilizing force or the stabilizing moment comes from this force, the FL, which tries to make everything go in this direction. Right? So ideally, we want the stabilizing moment or FL to be greater than your pushing force or your pushing moment or your overturning moment. So ideally, we want FL, we want that moment to be greater than FP. So this is another way of putting it. So as long as this side is greater than this side, then it will remain intact. It will not tip over. So if we continue the expressions again, we could say L minus 0.5, which we obtained, should be greater than mu H. Alright, so given mu, given our approximate pushing height, we could determine what the base L should be. So we say L is greater than mu H plus 0.5. Alright, so to get mu, we could go to the internet. Remember, mu is the coefficient of rolling friction. Right, so we could go to the internet here and see. Right, so there are sites such as the Engineering Toolbox that could give us some basic charts, right? But nothing here speaks of a caster wheel. Right, so I found a caster wheel manufacturer that actually has some value here. So they have a nylon wheel on concrete, and we have 0.04, 0.3 to 0.03 to 0.04. So we will use that value. So we could say mu is equal to 0.04, use the higher end value. Right, we say H is approximately 1 meter. So we say that is just above waist-side where you would actually hold this thing and push. So now we could say L should be greater than 0.04 times 1 plus 0.5. So L essentially should work out to be greater than 0.54 meters. So as long as L, the base, is greater than 0.54 meters, so that's this here, then we say, and if we push in a nylon wheel on concrete, it should not tip over. So to be safe, we go over a little bit. We say let L equal to 0.6. So that way now L is 600 millimeters. So in terms of measuring cutting, it will be simpler to measure 600 millimeters as opposed to 504 millimeters. Sorry, 540 millimeters. Right, this is 540 millimeters here, as opposed to 600 millimeters. Right, so that's another thing in design. You always try to round off your values as much as you could. The values and figures that will be simple to measure and easy to cut. You have to avoid, a lot of times you try to avoid fractions or decimals. So it would be nice to have this at 1 meter, but that will actually be too big.